Alright guys, welcome in. This is Mr. Keener here with another video lesson. This time all about root functions, which we're going to learn about today. But before we get into root functions, let's talk a bit about square root and what this little symbol means. So this symbol is called the radical. Typically the radical means the square root. We're looking for what number times itself equals the number underneath. So we know that the number that when multiplied by itself equals 4 is 2. So we say the square root of 4 equals 2 because 2 times 2 equals 4. These ones are also square roots. Oops, I'll give you guys a second to find the square roots of each of these that you can. Alright, so the square root of 81 is 9. The square root of 9 is 3. The square root of 1 is 1. And the square root of 8 is, oops, actually that is not a perfect square. The square root of 8 can be simplified though to, let's see, we can break it down into 4 times 2. So 2 is not a perfect square, but 4 is. So since 4 can be broken down into 2 and 2, we're going to write it as 2 times the square root of 2. Not really relevant to this lesson, but still important to know. Just remember that the square root of 8 is not 4. It is one of those imperfect squares, as they say. All right, let's get into it. For our first exercise, we're going to graph the function y equals the square root of x. So in order to graph this, we're going to need to make a table. All right. Now, we're going to be strategic with the values that we choose for x. We're only going to choose values that are perfect squares. So we'll start with 0, 1, we're going to skip 2 and 3, and we're going to write 4, and we're going to write 9. So those are the first 3 perfect squares that we can see. The square root of 0 is 0. The square root of 1 is 1. Now you might think, oh, that was just x equals y. But obviously that's going to change once we get to 4. The square root of 4 is 2. And the square root of 9 is 3. So let's go ahead and graph these points. 0, 0. 1, 1. X is 4, y is 2. And when x is 9, y is 3. So we've got this shape right here. And you might be thinking, oh, kind of looks like a parabola, maybe like a little bit like an exponential growth function, but on its side, and you would be absolutely right. This does in fact match the shape of a parabola, but sort of tipped over. So we had a parabola and it fell down and it became a root function. And this is not a coincidence. This makes perfect sense, right? If we were to flip it around, if we're looking for y equals x squared, then these values would just be flipped. So when it's x squared, and we have the same x values, or actually we can go ahead and just flip the y values. When x is 1, 2, and 3, y is 0, 1, 4, and 9, just like that. So the x squared and the square root are, we call them inverses of each other, essentially. All right, let's move on. This is the graph of a root function, specifically a square root function. You know what? Just use the whole line there. Square root function. Oops. All right. You can use the graphing calculator to help you graph these. I would recommend that. But the square root functions all look like this. They kind of have this shape where they go up and they're increasing, but they're kind of increasing at a slower and slower rate, kind of the opposite of an exponential function. Exponential functions, you know, they increase at a faster and faster and faster rate, but these ones, they increase at a slower and slower and slower rate. All right, the domain and range. So the domain of exponential functions and quadratic functions were always all real numbers. But we can see from this graph that the graph is actually going to stop here at 0. And there's a reason for that. What happens if we try and take the square root of a negative number? Well, I know what you're thinking. Well, the square root of negative 1, shouldn't it just be negative 1? But what's negative 1 times negative 1? Well, it's positive 1. Long story short, you cannot take the square root of a negative number. Those numbers do not exist. They're called imaginary numbers, and we're not going to deal with those until Algebra 2. So don't worry about that for now. Just remember that you cannot take the square root of a negative number. So our domain is going to start at 0. And it's going to go to infinity. You can take the square root of any number as long as it's positive. So 0 to infinity is our interval notation. We have this right here because 0 is included. You could also just say x is greater than 0. Our range is likewise also greater than 0 because there's no way we can get a negative number when we square root something because we can't get a negative when we multiply to the same number by itself. Whether it's positive or whether it's negative, we can never end up with a negative number if the signs match. All right. So here's another square root function. This time we have a little bit extra, square root of x minus 2. So let's go ahead and do the same thing here. We'll do our x and y values. We'll do our function value here. I like this three-pronged table here. So x, we're going to do 0, 1, 2, 3 like we did before. But this time we're going to do the square root of x minus 2. We're going to put that in here. So 0 minus 2. Square root of x is 1. I'm going to do minus 2 there. The square root, oh, I messed up here. I didn't mean to do 1, 2, and 3. I meant to do 1, 4, and 9, similar to what we did on the last table. There we go, 1, 4, and 9. The square root of 4 is 2. The square root of 9 is 3. And we're going to subtract 2 from each of those as well. We're going to end up with negative 2, negative 1, 0, and 1 for our y values. Let's go ahead and graph those. So 0, negative 2, 1, negative 1, 4, 0, and 9, 1. So we have the same shape, but something has happened. If we flip back and forth between these two, we can see it's the same shape, but this graph has moved. What do we call that move? We call that a shift, specifically a vertical shift down. That's right, we're transforming. Oh, you didn't see that coming, did you? That's right, we're transforming these functions. If you remember, with our vertex form equations, we learned how to transform quadratic functions. Well, guess what? You can transform any function the same way. So when we go ahead and subtract 2 on the outside of the parentheses here, well, that's going to take the whole graph and it's going to shift it down, just like that, down 2 spaces. All right, the domain does not change here. We're still limited to all of the positive numbers, so 0 to infinity, or x is greater than 0. Our range, on the other hand, has changed. So it's still the same basic idea, but since we've moved the entire graph down 2 places, we're also going to move our range down 2 places. So now our range is negative 2 to positive infinity, or y is greater than or equal to negative 2. Oop, I made a mistake there. This should be greater than or equal to 0. When we have the bracket, that means greater than or equal to. The parenthesis means greater than. Let's go back and fix that over here too. Fix that on your paper. Fix it, fix it, fix it. Fix it, fix it, fix it. Nothing to see here, nothing happened. It's all good. I don't have time to go back and edit this, so we're just going to push on through. All right. Okay, so those are your square root functions. Now we're going to get into something that you may or may not have seen before, and that is a radical with a little 3 there. All right, so we said that by default the radical means the square root. Well, when we put a little 3 here, that means the cube root. So we know that x cubed looks like this. So when we take the cube root of something, like x cubed, we're looking for the number that, when multiplied by itself 3 times, is equal to whatever's under the radical here. So let's get some examples. Let's do some y, x, and y. All right. To get some examples, actually, we're going to work backwards. We're going to take some x values, and we're going to cube them and see what we get for y. So this is y equals x cubed. And let's do our 0. Actually, yeah, let's have some fun here. Let's do negative 2, negative 1, 0, 1, and 2. All right. So when we do x equals negative 2, we do negative 2 times negative 2 times negative 2. We're going to end up with 4 times negative 2, which gives us negative 8. So when x is negative 2, y is negative 8. When x is negative 1, now this is a fun one. When we cube negative 1, we do negative 1 times negative 1, right? Which switches it to positive 1. But then we multiply it by negative 1 again, so we just switch it right back to negative 1. Spoiler alert, if you keep multiplying by negative 1, all you're going to be doing is switching the signs back and forth. Fun stuff. But since we're doing it 3 times, we go negative, positive, negative. You can think about it that way. We start negative, positive, negative when we're doing negative 1. We end on negative. 0 times anything is 0. That was an easy one. 1 times 1 times 1. Boring. It's going to be 1. And then 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. And let's do one more. 3 times 3 times 3. 3 times 3 is 9. And 9 times 3 is 27. It's probably not going to fit on our graph. All right. So we can use the table of y equals x cubed to pick our numbers for the cube root of x. Let's go ahead and do that. All right. Now, let's choose the y values here to be our x values. So this time we're going to do -8, -1, 0, 1, 8. We're not going to do 27 because my graph ain't that big. All right. When x is -8, the number that we cube to get to -8 is -2. When x is -1, the number that we cube to get to -1 is -1. 0, 0, 1, 1. You'll see some consistency there through all the different types of root functions. And finally, when x is 8, that means that we've cubed 2, the number 2. All right, let's get rid of this because we're not graphing that. We're graphing this one over here, the real one. This is the real. All right, the cube root of x. That's how we call that, the cube root of x equals y. Equations. Doesn't matter the order. Typically, you want to put y on the left, though. My fault. I ran out of space. And now I'm taking so long explaining why I should have done it the other way. I should have just done it the other way. All right, here we go. When x is -8, over here, y is -2. When x is -1, y is -1, 0, 0, 1, 1. And then when x is 8, y is 2. All right. So this graph has such a cool pattern, and I love graphing it. All right. It looks a bit like, if we only could see, whoops, that's not right. I don't know what I was doing there. If we could only see this half of the graph, we see basically what looks like a root function, a square root function. And that makes sense because they are pretty similar to each other. But the difference between the root function, the square root function, and the cube root function is that the cube root function allows us to have negative numbers. And the reason it allows us to have negative numbers is because if we multiply a negative times a negative times a negative, we end up with a negative. So it's actually possible to get those numbers, which means we can cube a negative number. Can't square root a negative number, but we can cube root a negative number. All right. So that is what the graph looks like. The domain, because x can be anything now, our domain is back to our good old-fashioned all real numbers, -∞ to infinity. But our range is, what do you know it? It's actually also all real numbers. There is infinity cube. What's the cube? How do we get to infinity? Well, we just cube infinity. What's the cube root of infinity cubed? It's infinity. Okay, cool. Yeah, we can get anything we want for y. Eventually. I mean, we're talking about ridiculously large numbers. But the point being, there's nothing that y can't be. There's nowhere that it's going to stop vertically. All right. Oops, I shouldn't have erased that. So it's -∞ to infinity for both. That's the moral of the story. All right, last one. Here we are, the cube root of x plus 1. Okay, now in the last one we talked about this transformation. When it's outside of the parentheses, if we imagine the x is there in the parentheses, that's going to be a vertical shift, and it's going to go down 2. All right. Now this is essentially inside the parentheses. So what type of shift is that going to be? If you said horizontal, you are correct. Now, is it going to go left or is it going to go right? Now we are adding 1, and that means that we are going to be taking this entire graph and we are going to be shifting it 1 space to the left. I hope that wasn't too loud. I drum rolled on my desk. I got a little too excited there. All right. So let's go ahead and fill out the values. We're going to use the same values as before. We're going to use that -2. Oops, what did I do? Let's see. We're not going to use the same values as before. Instead, we're going to use values that when we add 1, we're going to get to the values that we wanted before. So we're going to actually subtract 1 from each of these values. This maybe gets you into an idea as to why exactly it's moving to the left. So x is -9, x is -2, x is -1, x is 0, and then x is 7. All right. So let's talk about why I chose these values. So -9 plus 1 is -8. The cube root of -8 is -2. -2 plus 1 is -1. The cube root of -1 is -1. -1 plus 1 is 0. The cube root of that is 0. 0 plus 1 is 1. The cube root of that is 1. And then 7 plus 1 is 8. And the cube root of 8 is, whoops, what the heck am I doing? The cube root of 8 is 2. Okay. So just remember that we are adding 1 before we take the cube root. Oops, didn't want to do all that. There we go. So x plus 1 8, negative 1, 0, 1, 8, which is what we had before. So we just sort of shifted everything to the left, just like that. And that's why that works. 2, 1, 0, oops, sorry, negative 2, negative 1, 0, positive 1, 2. If we graph that, so we ignore this middle column. That was just to help us. These are the actual values. Negative 9, negative 2, negative 2, negative 1, 0, 0, or sorry, negative 1, 0, 0, positive 1, and then 7, 2. Okay. Same graph, but shifted one space to the left. The domain and the range, they're not going to change. It's still going to be negative infinity to infinity for both. All right, that's all. Thanks for watching. Sorry this video went on a little bit long. Here are the pictures of Cha-Cha as promised. She really likes to eat hair ties. She puts those in her food bowl. She seems very proud of it. All right, have a good one, guys. Enjoy the rest of your weekend. Bye-bye.